For E, the degree is 3. 1, 2, 3. So they should have the 3 the endpoint A, C, D. Okay. So here is an undirected graph, and that's the bar graph or directed graph, digraph. Okay. But the digraph we just followed as it's the arrow way. So the first is also the text, and the second column is the terminal vertex. It is the same for the adjacent vertex. It is just for undirected graph and the terminal or endpoint. It is for the digraph, directed graph. Okay, so for the A, we should be careful. It is from A. That means from out. We just reach. It is a node. So we just to B, C, can reach B, and this arrow can reach C, and also from this arrow can reach D and E. And for here, we should be mentioned the D. Also, you will find 1, 2, 3, 3 edge connect with D, but should be careful. Here, it is just the adjacent list. We are only to consign from D can reach the end point. And from D, we will find it is all, this is a 3 edge, but all it is come in, no come from, no come out, no go out, no go out. So it is empty. For vertex D, there are no terminal vertexes because they are just all of them, it is come in, no come out, no go out, or no just the edge out. So for D vertex, they have empty for the terminal vertices. Okay, and for E, it is similar. You can order 1, 2, 3, 4, 5. We have the 5 edge, but here we just only consign the just the in degree. We have the mentioned degree, have the for the digraph, we have the in degree and out degree. So here we just to consider the in degree. Out degree. Out degree means that only here is out, and here is out, and here is out. Okay, for any the out edge to find its the terminal vertex. Here is B, and for this is C, and for this is D. So we only have B, C, D. Okay. We don't care about, although they have the edge from A to E, but here we just only to consign to the out degree. That means from E can reach, E cannot reach A. So A cannot stay in these terminal vertices in point E. So here is a adjacency list. Adjacency list just to consign all the vertices that are adjacent to each vertex. And here just consign the undirected graph or directed graph. Okay. And sometimes if we can also to using adjacent matrix, and here is just the adjacent, say the list just to similar as the table, and just list how many the terminal nodes from some the vertex. It is just from A, for example, from A can reach some the vertex or endpoint. And similarly, we also can just using for not simple graph. There may be some the simple graph, but if you just have the more just how to describe all this using the metrics to describe all the graph. So we just sometimes using the adjacency matrix. Adjacency matrix is similar to the list, but they have consigned not only the 0 and 1, but here should be careful for A to B. That means how many it is just how many edge 1, 2, 3. From A to B, we have the 3 edge. So here just list the number of the edge. So it is the value for the matrix. Adjacency matrix, it is referred to the number of edge. The number of edge connected with this Vi and Vj. For example, A and B, they have 3 edges, so here is 3. And we just find here C to C, that means C to C, they have just the loop or circle. They have loop edge. So here we just mark 1. They have 1 edge. For the C to C, should be here C to C, we just loop. So any other have no loop. So any other the diagram, this is value is 0, and only the CC, it is just the loop only. We have mentioned that for just the relation matrix. We just mentioned that relation matrix is similar for it, but here we just extend our relation matrix because for the adjacency matrix, it is just to connect all the edge number. So here, for example, you just find C, E, C to D, they have two. These two means they have the 2 edges, just like C, D, and connect C, D, we have 1, 2, we have the 2 edges. So here is 2. So we have the adjacent list. Adjacent list just to concrete to give all of their concrete endpoint. And adjacent matrix just to combine or just to counting how many is edge. For example, here is A to B. A to B just like this. Here, if we just use an adjacent matrix, A to B just only 1. So the value is 1. Okay. So it is the two, just the 2 ways to describe our the graph. The first is using the table or list to describe our the graph. So this list and the table can similar as the set. That means although we can use the map or just the graph to describe the relation set, and similarly, the graph also can be described by the adjacent the list or adjacent set. And the same, we also can use the matrix. It is the computer just very looking at a bit about the metrics or matrix communication. So sometimes we just use the metrics to describe the graph. Okay. And for the metrics, we have the second the special metrics or incidence metrics. And this incident matrix, it is just you will find is different from the adjacent matrix. Adjacent matrix, that means all the arrow or column, it is nodes, it is vertexy. But incidence matrix, it is just find the relationship between the vertexy and edge. So it is different from the originally or just the before sessions. Previous sessions we didn't mention about this relation. That means here we just to the vertexy and edge, just connect vertexy and edge. So it is very interesting. Instance matrix. So here just means that for each the edge for E1, because his edge we are just to mark or make the nodes the edge on each the edge. Here is edge 1, E1. E1 just connect the vertex 1 and the vertex 4. So for this E1 the column, and we just find it is connect V1 and V4. So only V1 and V4 they are marked 1. otherwise it's 0. So you will find each the column only the two, here is only the two, just only the two value, the 1, other is 0, because we know that each the edge only connect the two nodes. It is from the definition of the edge. So each the edge only have the two value, connect with two value. So two vertex. So that means the two the value 1. So here is a 1, 1, and here just the V1 and V4. So E2 connect 1, 4, or 5, sorry. V1, V4, or V5. It is just the edge 2, E2. And similarly, for example, this is E5 connect with 3 and with 5. So for the E5, the fifth edge just connect with 3 and with 5. So also only the two value 1, just to mention about the two vertices for each the edge. And the E6. E6 is just connect the vertex 2 and the vertex 3. So the V2 with 3 should mark the 1, otherwise 0. So it is just for each the column we can connect, or just to mark the vertex that connect with this edge. And what it means, the row, that means for example, V1, we are just find the two the values 1. That means how many connect the values 1, it is means it is edge. That means for V1 we have 1, 2, it is a degree. So degree is 2. So here is the 2, 1, 1. So we have the two values 1. So that means the degree is 2. So for each the row, we can connect the value 1, and it's the number of the value 1 is equal to the degree this vertex. So it is also very interesting. So it is too easy to using the metrics to compute our degree. But for our human, maybe you can to count for each the, for example, we 2, 1, 2, 3, we can count. They have the 3 edges. So degree V2 is 3. But for how to net computer cannot to see this picture in their computer the brain. Okay, just only to store the 0, 1 and 0, 1. So here, if we just using this incident matrix, computer can connect to counting how many the value 1 in this row V2. So it is 1, 2, 3. So it is means it is very quickly to compute its degree. So if we just using a good data structure, then we can very familiar to compute or to counting our degree. So that is why data structure sometimes is very important. So here we just using the incidence matrix. Okay, for the incident matrix, we can connect the vertex and edge. That means vertex and edge we also to consign or describe this matrix. So it is very interesting for this incident matrix. Okay. So for this, just the description. That means we have the two ways. The first, we just using the set or list to describe on the adjacent list, and also we can use the matrix or table matrix to describe our graph. So this matrix, we have the two special metrics. The first is the adjacency matrix. Adjacency matrix just to combine or to easy to look at how many edge between the two vertices, okay, or two nodes, okay. And we also have the second matrix, the incident matrix. Incident matrix just to give the relationship between the vertex and edge. And then for each the column, we can to consign which the edge connect the two special endpoint or just the vertex. Okay. And for each the row, we can to counting how many edge connect with this vertex. That means it is a degree, and to counting how many the value of the one, we can say it is a degree for this vertex. So instant matrix and adjacent matrix can just to describe or many the useful features or useful some the computation or computer to compute or to just to evaluation graph. Okay. Okay, now we just to move to the next topic. It is just the graph isomorphism. Isomorphism, that means because we know that many of the graph have just to different people maybe they draw different the shape of the graph and what they have the relationship, they are different the graph, whether or not they are same. So how to define the graph the same? So here we just say if the graph have the same structure, although they have the different the shape or different the state, but if it have the same structure, then we can say it is isomorphic. So isomorphic, that means it is have a map. This map means that we can just map each the node and also each the edge. That means they are just the edge and the node of a taxi just have a can one-to-one corresponding map. Then we can say it is the same structure. For example, here are the two graphs, G and H. Although maybe the shapes are different, or the picture they are different, but if you just to map, for example, U1 to V1, you can just make their refer and U3, V3, and you will find sorry, it is not V1 because V1 just to reach the V4. So V1 maybe we just to here just the 3. For example, the 3 just maybe here V1. It is 4, and here for each this if we just map here. Then here just to U1 and U3, and here we just to means that 3 is okay. And then here maybe this just map this is okay. So then you will find this, for example, U3 here is a map this, and U4 just to get this with 2. So then you can find this is just have the same structure. So sometimes if just for example, if you can imagine this edge can be moved, if it didn't to break down this edge, it can seem it is just as it is just as they'll have just can be extend this line. That means if we just from this edge to move to this, we didn't break down this line. We just only to change this position, then it is okay. That means if we just to move this V4 to from this bottom to top, and then you will find it is similar as, that means V4 just refer to U2, then you will find this is the same structure for these two graphs, although here is a difference. So it is just the two, that means the isomorphic. And sometimes we can say the top graph maybe in a network. We sometimes to talk about the top graph. The top graph maybe is similar. It is just means that it is the graph can be as the same graph or same network if they have just the isomorphic top graph. That means this edge you can to move anything except you broke down. If not broke down this edge, you can to move, you can to draw, you can to draw longer, and you can do anything. So that means this edge can be seen as if just to put the node of the text U2 down, for example here, if just to U2 1, and then you will find, you will get the edge. That means you can move the vertex or you can move the edge, but you didn't to change their just the edge the relationship. Means you didn't to change their direction, or you didn't to break down any the line or any the edge. You can to move their vertex position and their nouns about their edge, no problem. So it is just isomorphic. So we can say it is the same structure for the graph. Okay. So here is just means if you just want to determine whether or not two simple graphs are same structure, maybe it's difficult. But if you just to find the counter example to determine it's not isomorphic, maybe it's easy, because for the same structure graph, they have the three, this is features. They should be have the same number of the vertices, the same number of the edge. The degree of the vertex must be the same. It means the degree means their edge for each of the vertex. Each of the vertexes should have the degree should be have the same for the two graphs. Otherwise, you cannot map. You cannot find this isomorphic map. Is one to one, one to one. That means just to corresponding the map. So if just to determine they are same graph, maybe sometimes you should need the more task, but if we just find the difference, maybe it is easy. Okay, here is two special example. The first is here is the second example. Here is the first, and here is the second example. And also have the graph G and H. If G like this and H like this, although you will find this is very, you can same is same, but if you just using the move or just to get the top graph, can you find they are same or not same? It means their structure are same or not. And just to try to check with the two examples whether or not they are just have the same structure. That means same structure just like this. That means you can just move some the node or vertex. You can to get the same, have the same structure. And if for the formula means that you can find some the one-to-one corresponding map between the vertex and edge and to get their map. And just you can try and to say, that means if you find they are not, you give some the counter example. Counter example is okay. That means whether or not they are, for example, if it didn't satisfy one of these features, then you can say is not. But if all satisfy, we cannot say it is. It is. We should be consigned again to find some, to check more. If it didn't set one of them, then we can say it did not. But if I set, if I satisfy all of these features, but we cannot make sure it is same structure, we should to determine or to consign more and to make sure it is same. Okay. So for the first question, first example, maybe it is easy to check whether or not it's the same. Just to follow about these rules. Okay. So for the first question or for the first example, you can just follow about these features to determine whether or not it is. So I just give you this hint. So we can just to find or to give the, try to give this solution for the first example. If find is not, you can give some the counter example. For example, if it didn't satisfy one of these features, then you can say it is not. You can write down your answer or your finding solution in the chat room. So from these rules, we mean that if the two graphs are same structure, they must satisfy these three features. The first, it should have the same number of vertices. That means vertices, their nodes and edge should be same. Otherwise, you cannot have the same structure. Okay. And then the degree for each of the vertex should be same. Otherwise, you should find it is the same. So whether or not the example one is the two graph satisfy all of them. If it didn't find, if it just find one of them is broke down these rules or these features, then we can say it is not. And find some special counter example for these two graph. Now we first to check, for example, to check the vertices. And then we check edge. So First, we just how many the node or vertex 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so first the features they are all satisfied. So that means they have the same number of the vertices, nodes. And the edge here is a 1, 2, 3, 4, 5, 6. Here is also 1, 2, 3, 4, 5, 6. So the edge is also satisfying. And then it is satisfying the features 1, feature 2, and the features 3. We are check feature 3. That means for each the vertex they should have the same. That means the degree should be careful for all the vertices. Must be the same. Okay. Now here vertex for the degree, we just said this degree is 2 and A degree is 2, C degree is 2, and here is a 3, 1, 2, 3. Here is a 2. Okay. And now for the H, the vertex degree, for the degree B is 2, for degree A, 1, 2, 3, 4. And for degree C is 3, here is 2, here is 1. So for this vertex degree, it is we just list the degree, for example, the degree G, just say the G degree, we just using this set, it is 2, 2, 2, sorry, it is 3, 3, 2, 2, 3, 3, 2, okay. But for H degree, 2 is 2, it is 4, it is 3, it is 1, it is 2. So they are different. That means they should have same. That means that all the degree set should be same. But now you will find, we find 4 and 1. But here, for the graph G, we have no vertex whose degree is 4 or 1. So the first example are not same structure. Okay. Now, for the second example, and if just to check this similarly about these 3 features, the first, whether or not they have the same node. Yes. 1, 2, 3, 4, 5, 6, 8. It is have 8. 1, 2, 3, 4, 5, 6, 7, 8. It is also the 8. Okay. So they are vertices, or they are just the node. They have the same node. So also have the 8 node. But H, 1, 2, 3, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They have 10 H. And similarly, we also have here is 4, here is 4, 8, and here is just 9 and 10. Also have the 10 edge. So they have the same edges, same number of edges for these 2 graphs. Okay. Now for the third, we just find similarly we can say using the set G degree, and we can say it is a 2, it is a 3, it is a 2, it is a 3, it is 3, it is a 3, it is 2, 2. Okay, so we will find 2, 3, 2, 3, and here, because we have the 8 node, so we should have the 8 degrees. So the inside these the 4 vertices, we just have the degree, the 2, 3, 2, 3. Okay. And for the H degree, Here is 3, here is 2, here is 2, here is 3, here is 3, here is 2, 2, 3. So it is 3, 2, 2, 3, and 3, 2, 2, 3. So you will find, although their order is different, but they have a same. That means 1, 2, 3, 4. That means they have the four nodes have a 2 degree, and the 4 nodes have the 3 degree. And for the graph H, they have the same. They have the 3, they have the 4, 3 degree. And then they have another 4 vertices have a 2 degree. And here for the graph G have the same. So they also satisfy the feature 3. Then we can say these two graphs are the same structure. The same structure because we know that you are trying to move the node, trying to make they are same, but you will find sometimes you will fail. So how to check about or find their difference about this? So for example, we can just to remove all of this mark, maybe. Okay. So for example, for the A, okay, yeah. Okay. Now for the G graph, this A, that means because we know that for the same structure, we are just for each of the graph, we just only the vertex and edge. Okay. So now for the graph G, we are just concerned about this the vertex A. Okay. And vertex A for the edge, that means they are just connect B and D, and you will find B and D just have the degree 3. That means in graph G, for the A, they are connected to vertexes and whose the degree is 3. Okay, now, and for just here, because here is just have the, for A have the 2 degrees. So in the H, for the 2 degree just means this is a 2 degree, this is a 2 degree, here is a 2 degree, here 2 degree, okay. So if just the map or if just to refer, that means the A is just one of these 4 nodes. That means A maybe refer to X or refer to Y or refer to T and refer to U, but you will find each one of them. For example, we just assume A refer to T. Okay, this is seem the A in the graph G. And then you will find A can connect with U. You have degree 2. You have degree 2. But in graph G, they are connect both degrees 3 vertex. That means A cannot connect the degree 2 vertex. Degree 2 vertex. That means for in graph G, okay, for A is a 2 degree, okay. We can say A is a 2 degree. 2 degree because it means degree A is 2, okay. But in H, the 2 degree only have these 4, but each of one of them, they can connect another the 2 degree. For example, X, Y. T and U. They are just one of them. You can select. If you select X, then he can reach the Y, and here Y is have the 2 degree. And if you just choose U, you can connect T, and T have the degree 2. But in A, cannot find to connect the degree 2. They only can connect the degree 3. So it is not. So that means you find, and similar for C is the same. That means C, it is a degree 2. Degree 2. Degree 2, you only map one of them is 4 vertex. But C connect the edge connect with the C also both degree 3. But in one of them, X, Y, T, U can connect the degree 2 vertex. So you cannot map. You cannot find the same. Okay. Okay, 5 minutes break. Okay, we continue to talk about how this graph, and maybe this the next just the concept or next this session for this this knowledge of graph. Okay, and maybe just the next week we are begin to form our summary. Okay, and before and this net we are just to talk about our the final course report. Okay, because this is an online course, so we have no the offline the examination. Okay, so we are just give you this final report, this question, so you can just to write down or submit your final report, similar as some homework or just the examination or just the excel, I mean, just the report, just the practice. You just have the experiment report. Okay. Now, here just as I mentioned about this the same to determine whether or not the two graphs are the same structure. And for we have just have the three the features to determine whether or not they have the same structure. They should have the same node, same edge. They should have the degree of the vertices should also be have the similar or have the same. But although that, for example, the example one, they are set you that we can find some counter example for easily for this feature that set you find this one of the these three features. But although they are also set to find these three features, we cannot say it is the same structure. For example, the second example, we find these not same not the same structure because we find for this the 2-degree A or C, they are both connect that the 3-degree B or D. But in graph H, for the 2-degree, we only have these 4 2-degree, but each one can to find this 2-degree. That means each one to connect the 3-degree and 2-degree. And for here, X is connect 3-degree for X, for example, here X just connect 3-degree and 2-degree. And for Y is similar. They are connect 3-degree and 2-degree. But in the graph G, for this A and C, they are connect the 3-degree, only connect the 3-degree. So it is not the same structure. And similarly, we also to, because the same structure, sometimes we can to find the subgraph. If the subgraph is also not the same structure, we also can say or determine it is not. For example, we only to consign the 3-degree. Here is a 3-degree, 3-degree. And here is 3-degree, here is a 3, here is a 3. And then we just, for these 3-degree cell subgraph, that means we are just to draw this 4 node and edge. With 4 node and edge, then we can the subgraph here is B F, and here is H, and here is D. These. So this is the four nodes that have the 3 degrees, and there can be seen the subgraph. Okay. And for the graphed edge, what is the subgraph? So this subgraph is like this. Here, subgraph like this and like this. That means in H, they are just the 4 vertices that have a 3 degree. W, Z, B, and S. So you will find this subgraph for this degree 3, you cannot find their map this subgraph to each other. They are different. They have the different structure. This structure cannot have the same. This structure cannot have the same. So it is the other way to determine it. That means we can to draw about the subgraph and to check whether or not the subgraph are also the same. Okay. So it is all the concept, all the knowledge about our course. So the next, just to talk about the final course report. It means just from here, yes, like this. Okay. So yeah. So it is just the means. So the question maybe is simple. That means just the hope or expected you are using. Have already learned the theory or method or algorithm to solve out the special the question or problem in computer science. You can. It is the topic maybe is just the open. You can find everything, but your solution related to the course. For example, you are just some using the graph theory to find the shortest path between the computer network. For example, this is maybe is very simple, but you should to select all of them about to draw to write down your report. It means you are just using our course some the rules or theory to solve some the real question. And this question should be related to the computer science, maybe. Okay. And here just maybe some it is a requirement. That means you should do by yourself separately. You cannot copy the same. Just find the same, maybe both or just all of them should be just to have just the knower. Okay. And you should to describe well about your problem or about your question, and then how to solve. And we just hope or expected you are design some the pseudocode algorithm, and maybe possible you can to give your concrete the programming language or just the final the report or final output from your concrete code. Okay. And last part, you can just say a summary about your course or about your report from this just the solution. Okay. So it is just the report things. And before the continue, do you have any question for this report, the final course report? Okay, before you prepare your question, we just give you about the video, and the video just show you about how to use the graph to solve some question. These applications for the graph. Okay, to give you about your inspiration. Okay.
On the question, when am I ever going to use this? Which is how to apply graphs to problem solving. So suppose Adam, Ben, Chris, David, and Eric are training for tasks at work. Adam and Chris are training for task 1. Ben, Chris, and Eric are training for task 2. David is training for task 3. Chris and Eric for task 4. And Eric only for task 5. Create a graph to model this, and then we'll get to the matching part in a second. So if I want to create a graph to model this, I'm going to use Adam, Ben, Chris, David, and Eric. Adam, Ben, Chris, David, Eric. Those are my people. Now, obviously, this is going to be a bipartite graph because Adam is not going to learn Ben or Chris or David or Eric. Adam is going to learn a task. So now I have to put my tasks out. So my task 1, 2, 3, 4, 5. Now all I have to do is draw in the lines that connect the appropriate people to the appropriate tasks. So Adam, Ben, Chris, Ben, Chris, and Eric, I'm off. Adam and Chris are training for 1. So Adam, Chris, training for 1. Ben, Chris, and Eric training for 2. So Ben, Chris, Eric training for 2. David is training for 3. Chris and Eric are training for 4. And Eric is training for 5. So if I were...
So here just to using the graph to give this picture about to show or easily or frequently for this about this question. But here it is a very simple question to using for about the question by using the graph theory. Okay, but for your final course report, you should have some the more the complexity of the question, not just draw this picture. I just showed you example to this. Okay, and the next maybe example from this video have some a bit complicated using this graph. Okay.
We're just modeling this with a graph. I am done. Now it says determine if a matching is possible. And for matching to be possible, what I'm looking at is, can I assign Adam, Ben, Chris, David, and Eric each 1 task so that each task gets done? And obviously I have a well-trained person for each of those. So let's switch up colors. And I would start by looking at the singletons because there's only 1 person who knows how to do task 3. And so David gets task 3. And there's only 1 person who knows how to do task 5. And so Eric is going to do task 5. So David and Eric are out of it. And now I'm looking at Adam, Ben, and Chris, and what would be the best place for them. Well, for task 4, the only people who knew how to do it was Chris and Eric, and Eric's already taken, so Chris gets task 4. And so now can I assign Adam and Ben? Sure. I could either assign Adam to 1 and Ben to 2, or I could assign Adam to 2. Oh, no, I'm just kidding. No, that is the only one. I thought Ben also knew how to do 1. So yes, I can do a matching. That is my matching. So Adam would do task 1, Ben would do task 2, Chris task 4, David task 3, and Eric task 5.
So here just show you about the simple example to using the graph to get your matching task. And here just maybe you will find he just try 1 by 1 and just to consult before their conditions. And in the future, if you just write down your final course report, the first you should to select some question, and this question may be it is hope or expected related to the computer science, and then it is your solution should be can summarize some the basic rules, not just the very concrete. You should to abstract some the general rules, the general solution for this the popular question. It is good. So you should to summarize or should to abstract some the similar as the algorithm or the pseudocode, and maybe some just the diagram, the flow diagram maybe just similar as you have the other course such as the algorithm, the structure, or some the program language course. Maybe you also mentioned to solve some the concrete example using the flow chart. Okay.
Okay. Adam would do task 1, Ben would do task 2, Chris task 4, David task 3, and Eric task 5. So this will resonate with all of my computer people out there. Suppose we have 8 devices, computers, printers, etc., that must be connected through a local area network. And I just want to look at some of the ways that this might be done. So one way that it might be done would be with my 8 out here. And then like we had talked about before, kind of like our wheel, but instead of a wheel, we're not going to connect any directly to one another. We're just going to connect everything to the middle. So that would be one way to set up a network. Obviously, this is a great way, but if this guy goes down, now we've got real problems, right? We can also set up a ring, and a ring is really just a cycle. And a cycle is just fine, but the problem with this is, let's say this guy is a processor. Well, then for this guy down here, it would take a lot longer to get down here as opposed to the star model where each is directly connected. The hybrid model, obviously we all know the connotation of hybrid, but the hybrid model is going to be basically the ring and the star. So this one is better because we've got, if something happens to the guy in the middle, we still have other ones that might take longer, but basically it just provides a little bit more strength. So sort of continuing along that train of thought, now I have 9 processors. I want to carry out some sort of algorithm, describe the different ways I can arrange the processors and the advantages or disadvantages of each. So obviously I could do a linear array, 4, 5, 6, 7, 8, 9, and a linear array obviously is just everything in a straight line. Now, does this work? Of course, but it sucks for these people at the end because if it starts down here, it's going to take a really long time to get down here. A mesh network, we'll actually come back to mesh. Let's look next at the complete. So a complete would be just like you think it would. We would have 9 points, and everyone is this is going to be really messy. I'm just giving you the heads up ahead of time. Each one of these points is connected to each other one of these points. Now, is it okay to do it that way? Well, sure. But what's the problem with this method? Well, if you think about every line that I'm drawing being, say, like a fiber optic cable or something like that, then I'm spending just so much money just to have this very robust network. I think I probably missed a few, but you get the point. You wouldn't want to create a network like this because it would be very costly in terms of time and upkeep and everything. So a mesh network is actually a really good way to go, which cuts down on the fact that it's not linear, but we still have a lot of extra connections. So we can sort of partition out the work into different processors to get the work done more quickly. So mesh network is a better way to go.
So here just to choose some the different network using the the graph. That means this is different. This is the linear, just similar, have the line. This is a graph, and here is just as some the mesh, the graph. Here is a complete graph, but you will find maybe this is easy to find each one because each node can be connected, but you should be careful. It will have the more expensive. That means you should connect the network, or sometimes it is should to arrangement, or just keep the store, or keep the just the arrangement. Many of these the network, it is boring for that. And for the linear, maybe it is simple, but it is cheap. But sometimes if you just want to check, you just reach one of them, you should to long time. So the mesh network, just the balance about the economic and some just the efficiency. So it is best on like this. Okay, so it is just to give you the concrete example for some the application of the topic. And here topic is the graph. That means the graph the application. Maybe in the previous sessions, we also just, for example, the probability, and for the counting rules, we also have the many the applications. So in the final course report, you can choose one of the rules or one of the just the theory. You can just to write down about your algorithm to solve some the concrete example. We hope this example or your question related to your major, just the computer science major. Okay. Okay, now it is just to give you the question time about our course, or just this final report. And the deadline for submitting final report is before New Year. Okay, that means December 30. Okay. Yes, December 30 or 31. This is just to have the new topic, is the new topic, and this Friday we have the last experiment. This Friday we have do your practice time, and the next week we are just do our summation overview of the all course, because I just give you the more time to prepare for your final report. So today, or this session, I just publish your final report question and requirement. So the next week, we are just summary or overview of the whole course. Okay. And this Friday, we are just the last experiment, or experiment 4. And then I'll publish the experiment 4 report the homework. Okay, you're welcome. So altogether, we have 7 homework. and the 4 experiment report, and the last the final course report. That means we have the 7 homework plus the 5 report, the 4 experiment report, and last the final report. And the final report, maybe it is a person is 40%, and your just the before about together is 60%. This 60% includes your homework, your just the sign in, and your experiment report. So you should to prepare well for your final report, because the final course report, it is occupied about the 40% for your whole score. Okay, the question is, same report, I didn't send it on time. Same report, what means? Just, you just want to say some report or same report. Some report, you didn't send it on time. So if you didn't send it on time, you can to connect with the teacher assistant. You can to send him. It is also okay. Okay, yeah. That means if you have any question to submit your homework or your report, you can connect to the teacher assistant and then to send him by email or just by DINTALK message, no problem.
তোরা কোন দিশে ঘুম পায় কতবার ডাকলাম ভাত পানি দেবা নাকি ঘুম পড়ি পড়ি তুই বুঝলি
So here is a teacher assistant. The 2 teacher assistant. And if you just have any question, you can send this teacher assistant for the homework and report. And here is a sign in. If you have any sign in question, you can connect this teacher assistant. Okay, and this is just to connect for helping you about your homework or report. Any more question? Okay, the question is, we have just the full experiment report. This Friday. Yes, we have the full experiment report and the final report. They are different. Okay, so all you should to prepare for it. Because the last Wednesday you have already to done for your just the experiment 4, last experiment, and this Friday you will have already. You can just publish this experiment 4 homework. You can submit. Experiment report is different to our final course report. Experiment report just to let you to implement existing algorithm, but the final report you should to design your own algorithm to solve your own the question you are selected. Experiment report will give you the question and also sometimes give you the pseudocode algorithm, such as experimental 2 or 3, just to give you the pseudocode algorithm. Yeah, just implement it, okay? But final report, it can be seen as combine all of them. You should to select question and you should design your algorithm and then to implement, and finally you can summary about this, okay? So the final report can be seen the whole process about the solution using our course theory. Okay, welcome. Okay, thank you. Welcome. Any more questions? Okay. So no question. That's all today. Bye bye. You're welcome.
그제から